Nah, it's my candy. But, oh well. So how's it going, folks? It's going? Yeah? How's homework going? Any questions that I can help you with?
Yeah.
Yeah?
Can you go to the section 6?
Section 6.
Yeah.
Here we are.
Can you explain how to calculate the specific effect size across different labels? Interaction effect across different labels.
Across different levels?
Yeah.
Yes, okay. So the term specific effect size, as I defined in the instructions, refers to some kind of pseudo R-square. So your task is to figure out which of the variance components should have been reduced by each of the terms. So I say should have because in practice, some of them may have gone up if the effect is non-significant. So we're sort of targeting what should happen in theory. In general, level 2 effects, so things that are all at level 2, so main effects and interactions will target level 2 random intercept variance. Level 1 effects and interactions among level 1 variables target level 1 residual. What happens with cross-level interactions, which I think is your question, it depends on whether or not the level 1 part of the cross-level interaction has a random slope. If it does, the cross-level interaction predicts that random slope variance.
So in this data, it's from the default stack settings, there's only the residual variance for the first level and the second level variance. So there's no first level variance showed in the default.
There's no which variance? I'm sorry?
The intercross, the variance explained for the slope.
For the slope, yes. You have to add that to the model to get a random slope at level 2.
So what is the command?
What is the command? Sure, I can show you that. So we were going to re-examine model handout 3B today to look at some of the matrix stuff, but we can look at the random stuff too. So a random slope model was shown in model 4, where in Stata, after your level 2 nesting variable, you write the name of the predictor at level 1 for which you want a level 2 random slope variance.
Yeah, I added that, but I didn't see there's anything in the output to show this slope variance. I found there's a covariance, but I didn't see.
Let me open the Stata output that goes with that example. I'll show you what it, let's see, yeah, good, I can zoom in just a second. Random effect. Okay, so this is the model then that has this new variable. And there should be, under the random effects parameters here, you should have a variance of the level 1 predictor, the variance of the constant, which is intercept, and then the covariance of the two.
So if there is an interaction between the first level range and the second level, the other variable.
The cross-level interaction is
so
not random.
Cross interaction.
Mm-hmm.
So I should see the values for the first level difference.
Yes. So if you were to put a cross-level interaction involving that variable that now has a random slope, that random slope variance should go down.
So that is the effect size.
That is the specific effect size. Yes. Now what if you put in a cross-level interaction for a level 1 predictor that didn't have a random slope? So let me get, we did this thing last time. I'll pull this up. So this was the model from the homework that we went through. So we're talking about, say, a cross-level interaction between center mean stress and person-level coping, another cross-level interaction between center mean coping with person-level stress. So each of those cross-level interactions will explain the random slope variance for the level 1 predictor that it goes with. But what if we put one here, for instance? What if we added a cross-level interaction here where this line doesn't have a U, meaning it doesn't have a random effect. Then what variance would that cross-level interaction have to explain instead? Yep, E. That's the only thing that's left. Okay, does that answer your question?
Yeah.
Yeah, okay, good. Other questions?
So it's a dual model. The homework is a dual model.
Yes. Today's Tuesday, yes, so tomorrow night. Yes. One other thing that folks are having problems with, I've gotten a couple questions about this. So section 5 examines the random effects of the person-level predictors. So then I asked, what is the test statistic for how person-level coping on anxiety differs across centers? So that, let's analyze that part of the sentence. How the effect of person-level coping on anxiety differs across centers. What is that referring to? What model parameter refers to that idea? Negative log likelihood is the test statistic, but the part that's highlighted here, what is that idea? What in your model tells you whether or not this is true? How the effect of person-level coping on anxiety differs across centers. No, I'm asking about the effect of person-level coping on anxiety. So that is a slope right there. I'm then saying, how does that slope differ across centers? So what am I asking for? I could have said varies across centers as a synonym for differs, or varies randomly. That's the, yeah. So I'm asking about the random slope. So it is a level 2 random slope for person-level coping on anxiety. So it's variance across level 2 units and the effect of this level 1 predictor. And so how do we test whether or not a random anything belongs in our model? Kayla, say it again. The change in the -2 log likelihood. The difference in -2 log likelihoods is supposed to be distributed as a chi-square variable, where the degrees of freedom for the chi-square is the number of added parameters. So when I go from a model that has only a random intercept to a model that adds one random slope, how many parameters have I added? And don't say one. If I go from a model that has only a random intercept to a model that also has a random slope of a level 1 predictor, how many model parameters have I added to get that new random slope? 2. It's the variance of the random slope plus its covariance with the intercept. Because the random intercept and the random slope come from the same unit, they get to be related. Always, always, always. So -2 log likelihood is a chi-square variable. In Stata, if you do the LR test, it is given to you here. So I stored the estimates from the fixed model. I then compared them against the estimates from the random model, and you get this LR chi-square 2. So that is your likelihood ratio test statistic that is treated as a chi-square with 2 degrees of freedom. And that's the test statistic, that's the p-value that goes with it. Now what if I add another random slope, such as how the effect of person-level stress on anxiety differs across centers? If I add a second random slope, how many degrees of freedom have I added to the model? How many more terms have I estimated? And don't say one. 3 more. It's the random slope variance of the second predictor plus the covariance with the first slope and the covariance with the intercept. Yep. So there, you get extra homework questions just for coming or watching the videos. So this -2 delta LL, that is your indication of difference in -2 log likelihood. So,
According to the result of an art test, how can we say that it is better or
better or worse? So if you are adding parameters and the new model likelihood ratio test is significant against the one with fewer, then you have made the model significantly better. If you add something and the likelihood ratio test is not significant, then it is not better. The worse and not worse is in situations where you're starting with a model that has more stuff in it and you're taking things away, such as in factor analysis, such as in invariance testing, and a few other cases where you start with something more complicated and you're trying to see if you can simplify it without hurting fit. Then it's a worse, not worse. Yes, questions?
Yeah, I have a question about the interclass correlation because I was just I read more about it online, and so I found Wikipedia is not reliable, but it said describes how strongly units in the same group resemble each other. Isn't that wrong? Because I thought it was between groups.
No, that is correct. The wording is not as specific as I would like, but the sentiment is there. The 2 ways you can interpret an interclass correlation is the proportion of total variance that is between groups, which is the way you're thinking, and that is correct. But it is also the expected correlation of people from the same group.
All right, if you say the expected correlation, would that be the same as saying the effect then?
Yes, in the sense that the reason that they're correlated is because some groups have a higher mean than others, and that is what is inducing the correlation. So the effect of the group in a constant way, it's a constant shift that's causing the correlation. If you have a random slope, that implies a non-constant shift that causes a differential correlation across people from the same group. So that's actually what we're going to look at today. Okay, speaking of things that you read that aren't trustworthy, Hansi? So do you want to tell about the question you sent me?
Yes. So I was reading a paper for something completely unrelated, and they were looking at whether taking a sociology class makes you more empathetic. And they looked at a bunch of sociology classes and a bunch of other science classes that I think just undergrads were taking. And they looked at people's pre and post, like some empathy score. And they had lots of classrooms, like 20 sociology classrooms and like 20 science classrooms or something like that. And they said that they ran an ICC and decided that you don't need to do a multi-level model. And then actually I found this after I sent the email to you. In the conclusion, they said that they thought the teacher would matter for like how much empathy you have.
Oh.
And because of the ICC, the teacher doesn't matter.
So they said the ICC is small or non-significant. It was unclear, right?
Yeah.
If I were reviewer 3, I would have jumped on that, but whatever. And they gave some article as justification for ignoring the dependency. It was a textbook. Okay. So did you look it up? Did you see? No? Okay.
No, it was a text, so I figured it's probably somewhere.
Yeah, so it's like 600 pages, and somewhere in there is a justification for why you're going to ignore the multi-level structure in your data. ACEs. Okay. And so, and why is that bad? Right? We talked about this actually. So design effects. Remember design effects? It is an index for how screwed you are by your clustering in terms of your dependency. And the design effect is a function of the interclass correlation and the sample size per group. Only when the ICC is exactly 0 do you not have a design effect to worry about. So as long as it's anything above 0, there is at least some dependency there, which means your standard errors for your predictors have to take that into account. Now, the other reason why that's a bad idea is that what happens to the intra-class correlation depends on how good your model is at each level. So what happens as you explain level 1 residual variance? Do you remember? What happens to level 2 variance? Let me find it. This. If you explain level 1 residual variance, it will make your level 2 random intercept variance go up. They are yoked together because level 1 residual variance is used as a correction factor that adjusts the between group variance for how much is supposedly due to chance. Less within group residual variance means less of an adjustment, which means the level 2 variance goes up. So what that means in practice is, let's say that you have an intra-class correlation of 0.01. What does that mean? So kids in sociology classes, that's the structure. So 1% of the variance in empathy is due to, the answer is not in here. So if I have an ICC of 0.01, in her study that she's reading about of empathy of students nested in sociology classes, ICC of 0.01 would tell me what? It's between groups. So the proportion of total variance in empathy that has to do with mean differences between sociology classes. So 1% between class, 99% within class. Meh. That seems like, yeah, group is trivial. I'm just going to ignore it. You know, somebody, I said so. But what happens if I start explaining that 99%? I put enough good predictors in there as to why some people are more empathetic. That's going to drive the level 2 random intercept variance up, and the design effect goes up with it. Now, the other thing is the potential for contextual effects. To the extent that there's any differences between groups, the level 1 predictors have the potential for different level 2 effects. And so anything that they talked about as an individual effect that they only thought was of interest is probably biased by the stuff they didn't model. So yeah, Google University, Wikipedia University lets you down. But this is exactly why I'm so happy that you brought this up, because this is the kind of critical reading that I hope you can engage in as a result of more fluency with these models.
Why do we test the ICC for, so like in our homework assignment where anxiety is the outcome, why do we test an ICC for the outcome and the predictors? I know that that's probably an obvious question, but I don't know.
It would be some kind of empirical justification for the idea that you need to model the effects of your predictors at each level. So, I mean, it's one of those things that there's only certain contexts in which someone would expect you to justify that, but that is how you would provide a justification, is a significance test. But I'm saying even if the significance test is not there, if there's any variance whatsoever, I think you have to worry about it. So using the ICC is predominantly a descriptive statistic. It's introduced at the very beginning of a results section or possibly even a method section because it's going to change as you add things to your model. So it's not something to like die on, you know, that experience.
Well, I was having a hard time understanding how I would interpret that since they're not really the same kind of variables.
They are level 1 variables.
No, I meant like in terms of outcome and predictor. Unless
For the same reason that you can't ignore potential random intercept variance in your outcome, you cannot ignore the potential differential effect of the person mean of a level 1 predictor. It is literally the same problem. when we're forced to only model one outcome at a time, we have to solve that same problem in two different ways. The outcome gets its variance partitioned, and we do it manually through observed variables in the predictor side. Once you switch to a multivariate framework, we can treat outcomes and predictors the same way. Let there be random intercept variance and residual variance in each, and look at relationships among those variances directly, latent variables rather than observed. But we're not there yet. So does that help? Yeah? Maybe? Okay.
So when you build a model like you check like all your like predictor, level 1 predictors. You check like if all level 1 predictors like have an ICC or not. And if it has an ICC, like you make like you do like a group mean sometime.
You have to put the level 2 mean in the model somehow. Whether you pair it with a group mean centered level 1 predictor or not depends on whether you want the level 2 mean to carry the contextual effect or the between effect. But I tend to err on the side of if there's any variance in the across level 2 at all, whether or not it's detectable by an ICC, I put it in the model.
So going back to like our example, like so actually it's gonna be like 2 levels, like 3 levels, because like there's a pre-test and post-test, right? And students and like a sociology class. So like so also say like they check like 2 levels, or like it's a level 2, like they sort of they don't have to like include level 2 because ICC is 2 level. Or like I'm still wondering like if it's gonna be like 3 level it's better, or like 2 level it's okay. Because like looks like a time like a pre-test and post-test like could be level 1. Student level, like any background could be level 2, and sociology class could be like level 3.
Yes.
I'm just wondering, like, how many levels might be ideal?
If you wanted to predict pre-test and post-test at the same time, you could either think of that as 3 levels or as 2-level multivariate.
Okay.
And the difference is whether or not you let the variance at each testing occasion differ. Just adding it as a level implies a random intercept, which implies compound symmetry, the same variance across occasions. Whereas if you treat it as separate outcomes, the convention would be to let a different variance at each occasion. So kind of like a MANOVA sort of thing, but a multi-level version. One is nested within the other, but it's just a way of talking about it. You can predict each at the same time. But yeah, no one would ignore the fact that multiple tests come from the same person, but they are ignoring the fact that multiple people come from the same class. Yeah, so good catch. So that's one way people can screw up multi-level designs. Smooshing is the other way, right? If you're reading an article, how do you know if someone has committed the cardinal sin of smooshing, meaning conflating their between and within effects into one parameter?
They have like both the level 1 and level 2 for one variable, but only include one level for the other.
Yep, if you have a level 1 predictor and there's no mention of the level 2 version of it anywhere, then that level 1 predictor either doesn't have any level 2 variance and it's okay, but if it does, not okay. So that's a dead giveaway as well.
Can you give an example of that? In like a study example,
I could give you a whole bunch of examples. I've written about this extensively because it's so rampant. One that people don't think about is in accelerated longitudinal designs. Are you familiar with that as a concept? So that's like if you start, let's say you go into grade school and you grab first, second, and third graders and you follow each of them for 3 years. So then you have cross-sectional variance in age and longitudinal variance in age. And in theory, you can track the trajectory from first grade all the way to 5th grade, even though no one kid gave you that whole full information. In that case, people would just put grade in the model and form a trajectory from 1 to 5 and call it good, but that's a smushed effect. Because there's cross-sectional variance in age that is between persons in grade, the 1, 2, 3 that you started, and then there's the change within persons that's longitudinal. And those are 2 different things potentially. To the extent that like this year's 3rd graders are different than last year's 3rd graders, you have a problem. So that's a common one. Anytime people claim to be looking at individual characteristics and they throw a random intercept in the model to get to control for a group and they don't ever deal with it again, to the extent that people are not randomly assigned to their groups, to the extent that some groups have more people who are like this or more people who are like that, that tendency has an extra effect that belongs in the model. So it's all the time, pretty much. It's very rare to have a level 1 predictor that doesn't have any level 2 variance in a multi-level design. So, all right, other thoughts, questions? All right, then let's see, what are we doing today? I know what we're doing. We're doing matrices. Yay! But I promise you don't have to like do anything with them. I just want you to see this stuff so that you have a little bit of a sense of what's going on under the hood. Because I'm talking about sort of these piles of variance, and this predicts that, and this predicts that, but at the same time, these things are working to handle dependency. Remember what handle means? It means you don't know what you're talking about. So handling dependency is inducing a particular type of correlation structure. It's saying how your observations get to be related to each other. And it's a different structure if you have random intercepts versus random slopes. And so that's what I wanted to show you. So in reviewing, let me find my vocab sheet here. Make sure that we have our levels in place before we start this. Let's see, am I recording? Yeah, I'm recording. Sometimes I forget. Come on. There we go. Words and symbols for levels, right? We did this a while ago. We're going to add some stuff. So level 1, within, so person level stuff in the context we've been talking about, intra-group variability, represented by E residuals in the model, sometimes R depending on your textbook. The name for the matrix where the residual variance and covariance across persons live, do you remember? What letter? Nope, R. R is level 1. What's level 2? G, yes. And what do you call it when you put them back together again to talk about the total pattern of variance and covariance across persons? V. Yep. G and R. Welcome to the jungle, baby. We got fun and games. We got everything you want. So these are letters that are going to show up here. So R holds the level 1 variances and covariances. G holds the level 2 variances and covariances, and to put them back together again, you end up with V. So let me show you what this looks like in a random intercept model. So we did a little bit of this last time just to give you the concepts and the math at the same time. When we fit an empty model to begin with, so this, we add a random intercept to the model. We are not explaining variance, right? We are partitioning. We're not explaining in the sense that we know why some people have higher Ys than others. We just know that some groups have higher means than others, and that needs to be part of the model. And I can test whether or not the part of the variance that's due to between group differences is significant. That's your likelihood ratio test against your E-only model that's provided by default in your output. So in example 3B, I asked for some extra pieces of output to help show you what this looks like. So this is purely pedagogical, not something that you would typically do for an analysis because it generates a whole lot of output. But I'm on model 1 in example 3B, so this is page 3, just a 2-level empty model. We're predicting math at this point. So the random line in SAS, or the empty part here after school ID in Stata, that's where we tell it which random effects we want in the model. Stata gives you a random intercept by default, so you don't have to write it, whereas you do have to write intercept in SAS. Options are after the slash in SAS, and I am asking for the G matrix to be printed. I am also asking for the V matrix and the correlation version of it for the first group in my data set. Each group gets their own predicted V based on their sample size. So this will vary based on which group you have. In Stata, the analog is given by these E-stat things. E-stat recovariance looks like covariance it again? No, what does RE stand for, do you think? Close, random effects. Yeah, random effects are random errors, so I'll take that. So it wants the random effects covariance matrix at the level of school, because if you have more than 2 levels, you have to specify, but this is good practice to get into. It also gives you the W correlation covariance as an option. That is the correlation of people from the same group. That's your V matrix. And this is the original V. If you don't have the covariance option, then it's the actual correlation version. And I'm asking for it for the first school in the data set, which it's literally the order in SAS, and it's the ID in Stata to get the same output. So this is what I end up with. I have 2 numbers that comprise my model for the variance. In the empty model, the variance across schools, in this example I have 94 schools, is 45. The variance within schools is 253. The intraclass correlation of 45 divided by 45 plus 253 is 0.15. So of the total variation in math across students, 15% of it is because some schools have higher mean math scores than others. Said differently, 0.15 is the expected correlation of students from the same school. Now those 2 numbers, I can show you where they go to build that correlation. So first off, this is my R matrix. I've noted that it's truncated. It's actually a 35 by 35 matrix because that's how many students are in school 125. If you want to see the original, let me get the Stata output here. There it is. That's that is the W correlation. R actually doesn't show up in Stata for whatever reason. I can't get an R matrix. I can get G and V though. But here. So this is saying that the residual variance across people is 253. So everybody gets the same variance, and there is no covariance whatsoever across people. Because the model is saying after we control for group mean differences, people are unrelated. Level 1 is the same type of assumptions you make in typical regression. Normality, constant variance, and independence of the E residuals. So this is level 1 R. Level 2 G is not really a matrix. It's 1 by 1. It's a scalar. That's because we only have one random effect, the random intercept, whose variance is right here. If you take this random intercept variance and shove it everywhere in the R matrix, how's that for matrix multiplication, addition, and such? Shove it. I invented a new operator. It looks like that. Now, for those of you who are dissatisfied with shove it operators, here's how that actually happens. On slide 45, the G matrix is pre-impulse multiplied by a vector of as many ones as you have in your R matrix to make them the same size to add together. Or shove it. You know, you take your pick. It looks like this. If find this. So on the diagonal is the sum of the random intercept variance and the residual variance. That's the total variance for each person. On the off diagonal is the random intercept variance. That is what creates the covariance between people. If I take 45 and divide it by the 298, I end up with the correlation version of this and with a special number in it. That's my interclass correlation. So the model predicts that everybody from the same group has the same variance. Everybody from every group has the same variance, and that people from the same group have an expected correlation implied by the random intercept variance. It's constant, doesn't matter who you are. So that pattern is what the model says your pattern of dependency is. Constant. Only due to group mean differences, which are accounted for by the random intercept. So schools differ from each other only in the means. After that, people are independent. Okay, with me so far? So then we added some predictors. We had the smushed model, which we're going to skip. We added lunch at the school level and at the individual level. So school level lunch accounted for random intercept variance. Individual level lunch accounted for residual variance. And then we added a random slope. Now it gets interesting. Not that one. So we still have an intercept variance. Where did the random slope come from? It came from the residual. So now we're saying that schools differ from each other in two ways. In their intercept and in their effect of the level 1 predictor. So now there's two reasons why people from the same school are correlated. They are correlated differentially as a function of their value on the level 1 predictor. So the model then changes to look like this. We went over this last time, where we have the X matrix has all of the variables that have fixed effects. Gamma are the fixed effects. The Z matrix is all of the variables that also have random effects. So in this case, we have an intercept and then a level 1 predictor X. U holds the random effects themselves. So the predicted pattern that you end up with for how people from the same group are related is a complex function of the mean differences between groups plus the values that the people have on their predictor that has the random slope. It's a quadratic function, actually, that says the variance increases relative to some minimum as a function of the linear slope. The pattern then, to get to what V looks like, Z has two columns, and so it's a little bit more complicated than the stuff it operator that I demonstrated previously. But in the example, there are only two possible values for student free lunch, 0 or 1. That means there's only two possible kinds of correlation. So this is what we end up with. Here's my R matrix again. It has less variance in it because some of it was explained by the fixed effect of free lunch, and the random slope variance for free lunch was taken out of it to become a new variance at level 2. So here's G. So G is my level 2. It's the variance and covariance of my random effects that vary across schools. So the random intercept of 20 here, this is now the differences between schools and their intercepts, specifically when the random slope predictor is 0. So this is specifically amongst students who pay for lunch, don't get it free. 12 is the variance in the slope that carries the difference between free and reduced lunch and not. So it's the the detriment, we'll say, of getting free lunch to your math scores. 12 is how much that detriment varies across schools. And then the covariance shows up with it. So when we add a random slope to the model, such as sticking free lunch here or sticking it here, we are adding not only its variance, but its covariance with any random effect that was already there. That is not a default, folks. That is another thing you can do to screw up your multi-level model. I have fixed it with this command right here, type equals UN, and in Stata it's covariance UN as an option. What that is saying is that the G matrix itself, the matrix of level 2 random effect variances and covariances, is unstructured. Do you know what that term means? No? Do you know what that term means? Unconstrained. Everything gets to be whatever the hell it wants. That's what unstructured means. That's what it means. And that is because that's the only thing that makes sense for a level 2 matrix. It's simply saying that the random intercept variance can be whatever it needs to be, the random slope variance can be whatever it needs to be, and the covariance can be whatever it needs to be, including not zero. The covariance is a function of where the intercept is too, so it's conditional. So now, the V matrix for this one school, but it would look the same for other schools. This is a 35 by 35 matrix that describes the pattern of correlation, or variance and covariance in this case, across the 35 students from this one school. And I have labeled what each student's value of the predictor is. So the total variation across students, when you put levels back together again, is 246 amongst the students who get free lunch, and it's 257 amongst the students who don't. So non-constant variance across students. It was constant when all we had was a random intercept. It becomes non-constant as a function of the random slope. Likewise, the covariance between students is non-constant. It depends on their value of the random slopes predictor. Translating those covariances to correlations, there's only a couple numbers here. 0.03 is the expected correlation of a student who does get free lunch with one who doesn't. The correlation between two students who both get free lunch is this one. And the correlation between two students who don't get free lunch is that one. So on the whole, what happens is that all of the reasons for the correlation between students, constant or non-constant, are supposed to be in this G matrix at level 2. After you control for those reasons, what's left at level 1? Differences between students that remain after controlling for school dependency, that's supposed to be constant with no covariance. People are conditionally independent after you control for their school's random effects. That's what this is saying. Is that correct? Meh. For those of you following at home, I just did a really big shrug with meh. I don't know. You can't know, actually, because there's no answer to come back to. There's no common covariance matrix that every school shares that we can say is the right answer. It varies as a function of the number of people in your school and the values of the predictors. So all we can do is keep testing new random effects to see if they need to be included to allow for yet another pattern of variance and covariance across of people from the same school. All right, how are we doing? So the correlations between people, in this case, are much smaller than they were initially. What was the interclass correlation when we started? Do you remember? 0.15. Now it's down to 0.04-ish. It went down because my model explained a whole bunch of the random intercept variance. It reduced the dependency. It reduced the interclass correlation. It reduced the design effect. If I were successful in explaining all the reasons why schools differ from each other in mean math, then this would get down to 0. Not likely, but easier to do if you don't have very much school level variance to begin with. Okay. So R is level 1, G is level 2, V is the combination of the two. It looks like that when you put it together again. In an SEM framework, G would hold the variances of your random, your factor variances and covariances, and R would hold the residual variances of your individual items. So you can estimate these models as structural equation models as well. All right. Okay. Questions? Yeah.
Can you explain again when the odd diagonals of the B matrix will decrease to almost 0?
So what's happening in these data is two things. On the whole, this off-diagonal correlation is much smaller than it used to be. The reason for that is because of the 15% of the variance that was due to school differences, this model, actually the one before it, captured, I believe, 70% of that. So it reduced that 15% down to this much. The reason why these are not all the same number is because the covariance between people from the same group now depends on what their value is on the predictor that has the random slope. It is, let me find it again. It is this function right here. So it works out that the expected covariance between two people from the same group still starts with whatever the intercept gives you, but then it adds to it functions of the covariance and the random slope variance that are related to the values of the random slope predictor. So non-constant in a U-shaped pattern as the predictor increases relative to some minimum.
Are the X and Y people?
A and B are values of the predictor with the random slope. So like if someone has a value A and someone else has a value B, this is what the pattern would be. So that's why in the example, let me find it again, there are different correlations based on whether the two people being compared are both zeros, both ones, or a mix of the two. And there'd be even more possible for a variable that varied continuously. It interpolates across values in a smooth quadratic function. Okay. Other questions, thoughts? So yes. So how do multi-level models handle dependency? That's the question. How do they do it? By introducing random effects, variances, and covariances that are supposed to be responsible for the dependency. That's how. Supposed to be being the key word. Then, conditional on those random effect variances and covariances, people are supposed to be independent. Likewise, schools are supposed to be independent. And if they're not, you need a third level. That then induces a correlation between schools that come from the same whatever level 3 is. All right. So now some more fun stuff. Estimation. Can I do a little bit of this? Why not, right? So it turns out for general MLMs, all we have to do is figure out what the parameters in the model for the variance are. Everything else is solved from that. So in terms of estimation, maximum likelihood, the name of the game here, or the residual version, either way. So what we need to do is figure out what V is. The process of estimating, figure out 3 things: the estimates, their standard errors, and then how well it actually fits the data. And these can be both absolute or relative. But everything that we're doing is based on the magic of the normal distribution. The models that we fit, when you invoke mixed in Stata or SAS, you are saying that the residuals at each level are normal. The next thing, 2 units from now, we'll look at generalized models for when that is not the case. So remember this, normal distribution? Stolen from Wikipedia, so I hope it's not wrong on this. But the idea is that it has 2 parameters, mean and variance. So if all you fit were an empty model, what you would get for the predicted outcome would just be the mean for the sample, and the variance of the residuals would be all the variance. After we go through and add predictors, we have a conditional mean for each person that's given by y hat, whatever the fixed effects say it should be, and then E variance is left over, and it's assumed to be constant. So I want to point out the y-axis here. This thing is likelihood. You can think of it as probability, but that's not technically correct for continuous things, but it is literally the height. This formula right here, if you plug in your residual and basically find the predicted mean for each person, find their residual and the residual variance, you can figure out how high you are at any level of x. And the process is trying to figure out the model parameters that make the sum total of everyone's data the highest. And it's doing it for one outcome at a time. In our case, what the model's actually doing is coming up with a multivariate distribution for each level 2 unit. So it's like the people are multiple y's, multivariate data in that sense. So the function that it uses to find height, likelihood, switches from this top line for univariate data to the bottom line for multivariate data. So I've tried to highlight the things that are analogous. Whereas univariate data is characterized by 1 residual variance, our multivariate data, multiple people from the same level 2 unit, is characterized by V. That's the level 1 and level 2 variances put back together again. We have multiple fixed effects. So that's a set of matrices here. V shows up here again. So we need to find the values of the parameters that make V, the random effect variances, the random effect covariances, and the residuals, that together make the data the tallest. So when you have a value for what V should be, you plug this in for a given group, you get an outcome. You get a number. If we believe that groups are independent, we can multiply those numbers together to get a combined likelihood, but it's easier mathematically if we take the log so that we can add them. So that's where we end up with this thing called log likelihood instead. So likelihood is on the top, log likelihood is on the bottom, but you can see they have the same sort of shape. Once you have a V matrix, you plug that in and out comes a number. If you take the log of that number and add it up across all of the groups in your level 2 sample, you end up with one total result, and that is your friend log likelihood that shows up on the output. Log likelihood is in a scale where bigger is better. More likely is better. So that's what Stata gives you. That's what M+ gives you. Certain procs also give that to you in SAS. But because we're going to have to take the differences in these log likelihoods times -2, that's the version that shows up in other programs to try and help you with that conversion. -2 means smaller is better instead. So the process of iterating here is trying to figure out what combination of random effect variances, covariances, and residual variance lead to the combined tallest data. And it tries them out, figures out how tall it is, tries a new batch, figures out how tall it is, tries a new batch, figures out how tall it is. The process of trying to figure out what to try next and whether or not you're heading in the right direction is hella complicated. I can only wave my hands at it, to be honest with you. I know it has to do with calculus, because what you're trying to do is look for the top of something, and the slope on the way there helps diagnose whether you're over it or behind it, as well as the speed with which you're approaching. And so that's the type of information that it uses to try and hone in on what is best. But when it starts to try new values and the total sum doesn't change very much, it decides it's done, and it gives it to you as your estimates. You will see error messages that say things like non-positive definite. Have you seen that error message before? That means broken. That's what that means. Your model is broken. There are 2 reasons why these models break, and it has to do with this V matrix right here. If you have a random slope variance that it thinks is 0, or it has a covariance between random effects that makes it go out of bounds for a correlation. Those are the 2 things that will break your model and result in this. So even if a random slope variance helps the model, which I have seen a -2 log likelihood that's different, that's significant, even if there's a 0, you can't keep it. And so if these things go out of bounds, that means that you can't invert this V matrix, and it has to work around that problem to do something else. So you will see non-positive definite in your log, and you will also see it if you print the G matrix and you get a dot and a 0 where your parameters should be. Once you have your estimates, it's whatever makes your data the tallest. We got to figure out how good those estimates are. And that, again, comes from calculus. It works out to be related to the second derivative of the function, which is the steepness, but it's inversely related. So more standard error means less precision, meaning flatter surface. You're not really sure if you're at the top, but it's as good as you can get. Now, here's why I'm telling you about all of this. In terms of diagnosing model problems, once you have V, what's V again? What goes into V? Put it that way. Random effect variances, covariances, and residual variances. Basically, all the things that go into the model for the variance that create that total pattern, that's V. Once you have that, the fixed effects and their standard errors fall out. They don't have to get found, is what I'm saying. That searching process that's iterative, it doesn't need it. The magic of multivariate normal allows these things to just fall out the same way they do in linear regression. So why this matters is that when you add lots and lots and lots of fixed effects to your model, it's not going to break it. What breaks it is random effects. Every time you add a new random effect, which means adding its variance and the covariance, that's adding more dimensions to this multidimensional likelihood that it's trying to find the top of. More things that it has to search across. And that's where things can break. So it's not the fixed effects that break models, it's the random effects. That is not the case when we get into generalized models, though. That's only the case when you're in normal land. Okay. So one other thing that's related to estimation, ML versus REML. The basic idea of the difference between these two versions of maximum likelihood boils down to the difference between population and sample in estimating a variance. Do you remember this? N versus N minus 1? This is the same sort of trivia that fell away right away, right? In intro stat, you learn about U versus Y bar. But we don't talk about that anymore, right? We just go straight to Greek letters, because even though everything's sample specific. But if you don't have to worry about estimating the sample mean to get your variance, you can use N. You haven't estimated anything yet. You have N degrees of freedom left over. If you did have to estimate your sample mean to get your variance, then it's N minus 1. And for every fixed effect that you have to estimate to create Y hat, the predicted outcome, it's N minus that many fixed effects. So if you acknowledge the fact that you are having to figure out what fixed effects are given your variance components, you're accounting for degrees of freedom, that's REML. If you're not acknowledging that, that's ML. So ML estimates of random effects are going to be downwardly biased by N minus K over N. If you have enough level 2 units, it doesn't matter. But that's why we use REML. Here's the math. I'll be honest with you, I don't understand this. I copied it out of a book. I copied it out of someone else's book to put in my book. I did cite them though. But what it works out to is that this is the extra chunk that shows up in REML, and that has to do with the fixed effects standard errors. So when you are comparing -2 log likelihoods in REML, if the models are on different, if their models have different fixed effects, they're on different scales. So this little piece here that's extra is why we hold fixed effects constant when we test new random effects. You can test whatever you want in regular flavor ML so long as it's nested. And by the way, once we leave normal land, everything is ML. REML is only a thing for multi-level models that have normal residuals at level 1. If it's any other kind of distribution at level 1, it's ML. If it's any model that you are running in a structural equation modeling package, it's ML. And if you are running it in Bayes, the Bayesian log likelihood that it uses, that works with the prior, it's the ML version. So ML will be prominent elsewhere, but we use REML whenever we can. Then model fit. How well do the predictions match the data? We don't know. That's the short answer. You can only get absolute fit in data situations where all the observations share one common covariance matrix, and you can estimate it unsaturated to see what it should be. One other thing that I wanted to tell you about is this idea of chi-square tests. In Stata, I don't know if anyone has noticed this. For instance, this is the test of a random intercept against a model without a random intercept, and it labels it chi-bar 2 with 0.1 for the degrees of freedom. If you do a likelihood ratio test for any other kind of model comparison, such as when adding a random slope, instead of labeling it chi-bar, it labels it chi-2. What's the difference? It's whether or not you acknowledge that the thing that you're testing has a null hypothesis on the boundary. So I'm going to tell you about this because there are about 20 people in the world who know and care about the difference. I am not one of them. But just in case reviewer 3 is, I want you to be able to respond to their comment and decide whether or not you want to care. So if we go from adding, say, a residual variance to adding a random intercept variance, for instance, what is the smallest value that the residual or the random intercept variance can be? Can a variance be negative? No, not in the most software. It won't let you have it. 0, right? What is the null hypothesis that we're testing? 0. That's a problem. So if we have the idea that in theory 0 is the middle and a parameter could be positive or it could be negative, except it can't be negative, then we got to adjust. The same thing is true for a random slope variance. 0 is the null hypothesis, but it's also as small as it can be. So here, in pictures, is the problem. On the bottom is pictures of the chi-square distribution for different degrees of freedom. Stole this from Wikipedia as well. The little pictures are from an article in Psych Methods from 2006, although this person is not the first person to write about it. They just wrote more than other people. Do you see this tiny dotted line versus this one? Do you see that? Okay. The dashed line is if you test adding a random intercept variance, which is one parameter, using a chi-square critical value of 3.84, which comes from degrees of freedom 1. That's that one. Versus using a mixture distribution that is theoretically more correct, because half of the time, if it were going to be negative, that should have been degrees of freedom 0, which is not a thing. It's like flat, there's no area. So it basically takes that critical value and changes it to be for p less than 0.1 instead of 0.05. So if you follow the straight line, the critical value for testing whether or not a variance is significant is 2.71. If you follow the dashed line, which is degrees of freedom 1, the critical is 3.84. So there are very few situations in which you would come to a different conclusion. So when does reviewer 3 have a point? If you said, my random intercept variance is not significant, my chi-square difference was 3. Technically, you should be using 2.1 and not 3.8, so they have a point. Because then you're in this tiny little difference between the two. That has never happened to me. But what if you test it and you say, my random intercept significantly improved the model, difference in -2 log likelihood is 8. And then what if a reviewer says, excuse me, you should have used a mixture distribution? What do you say back? Dear reviewer 3, I'm sorry for not being clear, but 8 is bigger than 2 and 8 is bigger than 3, so it doesn't matter. The same thing is true for adding random slopes. If you add a random slope variance and its covariance, the covariance is fine because it could go positive or negative, but the slope variance is the one that it could be not lower than 0. So it should be a mixture of degrees of freedom 1 and 2, which creates a critical value of 5.1 instead of 5.99, and there's the difference in those. So practically speaking, if you are under 5.1, it's non-significant. If you are over 6, it is significant by anyone's standard, and somewhere between the two is when you have to worry about this. I hate having to label mixture chi-square tests and explain what they are. So if I can get away with avoiding that problem, I will. So just know that all of the tests that my fit test things and what Stata does, it's treating it as the regular degrees of freedom, not the mixture. If you want to do the mixture, what you have to do is take 0.5 times the probability from the lower degrees of freedom plus 0.5 times the probability from the higher degrees of freedom. So you combine them. And it's harder to figure out what that would be in cases where you're testing more than one thing at a time. Okay. Last thing, missing data? Bad. You know what you should do? Not have it. That's another misconception that MLMs handle missing data. They don't. Any case in your data set that is incomplete with respect to its predictors and outcomes is removed from the analysis, the end. It's the exact same rule as in any other linear model. How to solve it? So I'll let you look at that stuff since we're heading out of time, but I just want to say the two options that you have, neither one of them is a panacea. you can treat the predictor as an outcome. That's what happens in multivariate models. That's what happens in structural equation modeling packages if you ask for it, in which case you can have missing data on it, but only if you're willing to make distributional assumptions, such as missing at random. The alternative is multiple imputation. You can do that, but recognizing that it also makes distributional assumptions while it imputes the data. And the other part that's tricky for multi-level is that you have to be able to anticipate all of the effects that you would eventually want in your model. Otherwise, the imputation procedure is somewhat biased. That includes random effects. What happens when you add a whole bunch of random effects to your model? It blows up. May not converge, may have things that are really unstable. So you would have to be able to overcome that problem to build an imputation model that works. So in practice, what I have done is avoid this problem by using listwise deletion. It is not a good idea, but the solutions to it in multi-level are things that are still under development. There's no one way to fix it that's going to work for every situation. Just know that if you have missing any level 2 predictors, the whole group is gone. If you're missing level 1 predictors, only that person is gone. And so in terms of the type of missingness inference that you can make, it's different across level 1 and level 2 for that reason. Last but not least, don't output U's. The random effects, the U's, you can ask for them in your software. Don't do that. In general, we don't want to take random effects that are latent variables and treat them as observed variables in some other model. The error that goes around them has to stay with it. So you will see this discussed in other packages or other sources. Don't do it. That's my grand finale. Don't do it. Yes, thank you. There. Thoughts, questions? All right, then you know what? We get to do something new next time. Did you have a question? Harry? No? Kayla? No? Okay.
I have a question.
You have a question. Okay.
So, is there outlier issue in MLM?
Yeah.
Okay. How do you deal with that?
At each level. Leverage, influence, all that stuff you can ask for in multi-level.
Okay.
I get squishy when I think about dumping people out of the model as an arbitrary decision. So I would tread carefully if you want to pay attention to those statistics as a way to dump cases. But yeah, in theory, the same stuff in regression holds just at each level. People use U's to help diagnose those sorts of things too. But right. So next time, then we get something new. We have cross-classified models. Hooray! I know. 2 level 2s at the same time. You can handle it. I know you can. All right. Office hours start now. Let me know if you need anything. Otherwise, homework due tomorrow.